Logistics network design with optimization models. In this lecture, we'll talk about how do we determine what's a good logistics network to have. And so the decisions we'll be taking will be about the number and location of facilities that make up the logistics network. The facilities can be production plants, distribution centers, cross-docks, or any other processing facility. And when we do our logistics network design, we have to figure out the number of facilities we need, what are their locations, what are their capacities, and which customers or markets will each facility serve. Once these decisions are made with some objective in mind, then we have laid out the logistics network, because now when we have determined the facility number and location and which customers they'll serve, we can know the flow of product through this network. So think of a supply chain where you have suppliers, maybe some component manufacturers, then an assembler or final product manufacturer, and then they ship it to some distribution centers from where product goes to retail or to customer homes. So all of that comprises the logistics network. Now, when we are trying to find the optimal logistic network with regard to some objective like minimizing cost or maximizing profit, it's not always that we consider the entire supply chain. If we are trying to optimize, let's say if our production is in some other country and we bring the finished goods into the United States and we are concerned with distributing the goods in the United States, we can make ports like the LA port or the port in Georgia our sources, because product comes to the ports from our international suppliers, and then ports become the sources, and then from ports onwards we figure out which facilities we need, how many we need. Even for ports, we can figure out in the model which ports to use. Okay. But if we have a choice where we have not decided where to place a manufacturing facility, and it could be overseas and we have multiple options, we can include that as part of the model as well, because you could have multiple levels of facilities, like a upstream facility which ships to a downstream facility which ships to another downstream facility. So you could have multiple levels of the supply chain modeled in these models. So as you can imagine, making all of these decisions can get complicated really fast. So we need to build computer models and have the computer figure out the best decisions for us. When we are doing this modeling to optimization modeling to figure out our logistics network, there are two approaches that are often taken. One is called greenfield analysis, and the other is called brownfield analysis. So greenfield analysis assumes that you're starting from scratch with no existing infrastructure. So you would use greenfield analysis when entering a new country or a new region to sell and distribute your products. So you have no facilities in that region, and you say, okay, what's the best way for me to distribute product in this region? Or you might have a current logistics network and you might want to figure out how far is the current logistics network from the ideal network that I could have had. And because maybe in future you want to open new facilities to move towards the ideal, maybe close some inefficient facilities or badly placed facilities. And the network you have currently may have come about as the company grew. So it may have been growing organically over several years. And as the company grew, you open new distribution centers, new production plants. And each time you opened a plant or a distribution center, it made sense for where the company was at that time. But now that the company has grown a lot, all of your distribution centers and production plants may not be the ideal size in terms of capacity and may not be in the ideal locations. And so you might want to do a greenfield analysis to figure out how far are you. Because if you're not very far from the ideal, you're achieving close to the cost the ideal achieves, then you may say, okay, I'm fine, it's too expensive to change things around, I'm good, it's good enough. Brownfield analysis incorporates the existing network as a starting point. So you give it locations of existing facilities, and you can tell the model which facilities it can close and which facilities it must keep open. So if you have distribution center, so which you are, it is acceptable to you to close them, you can specify that these are optional, you can use them or close them. And then if there are some production plants or other things where you're kind of locked in a long-term decisions, you've raised a lot of financing for that, and you may have had contracts which lock you in. And so you might tell the model, oh, these you have to use, these cannot be eliminated. And that's called brownfield analysis, because you already have some facilities whose locations are known, whose capacities are known, and the only option you have is whether you have to use them, or some of them are optional. And a lot of times you have to use them because it's expensive to just close existing facilities and just open new ones if the benefit is not a lot. And so brownfield analysis is often done when the market or the demand has changed significantly. So you had a logistics network that worked for you in the past, but now the demand patterns have changed, or the demand has grown or shrunk, and now you want to re-optimize your network or change it a little bit to be better positioned for the current market conditions. It's often almost always done after large mergers or acquisitions. So let's say you acquired another company in the same line of business, and now the company you acquired has its own set of facilities. You have your own set of facilities. You may not need all of these facilities. So now you can run a brownfield analysis to figure out which facilities to close, which ones to upgrade, which ones to keep, and then you can optimize your network, because otherwise there may be too much duplication if you keep all the facilities from the acquisition in your existing facilities. So mergers, acquisitions often lead to this sort of analysis. Actually, even before a merger acquisition happens, analysts do this sort of analysis to see what the cost savings from the merger would be, because if these two companies are independent, they have their own networks, but when they become one company, there's overlap, and so some facilities can be eliminated, some can have more economies of scale, they can have a larger operations footprint, and so you can save cost sometimes by acquiring another company and then optimizing the combined network. So when we're doing these optimization, logistics network optimization, and you'll often be using some sort of software to do that. In today's lecture, we're just going to use Excel. Excel has a built-in solver for optimization modeling. And then, in the labs for this course, you might be using any logistics or some other professional software to do some of this stuff. So when you use this software, what is the data or information you need to have to build a model in Excel or in some of these software and actually do this in real? Okay, so you need to know where your material is going to come from. So location and capacity of suppliers. If you're just optimizing for a country and you don't have production in that country, production comes into that country through some ports or some border crossing points, you can make them as virtual suppliers, because your scope of the project is just to optimize the network in that particular country. And so you say, okay, whatever product I need for this country is going to flow in through these 2 or 3 ports or these 2 or 3 points on the border crossing points where it's going to come in. So I can mark that as virtual sources or suppliers. And then, I can then look at the cost from that point on within this country and try to optimize that cost. You need location and quantity of the demand. So the demand in terms of units that customers place on you and where are they located. Almost never you work with the individual customers, because you're going to have like millions or thousands or hundreds of thousands of customers. You'll often aggregate demand into geographical blocks. So you might go by zip code, like a 3-digit zip code or a 4-digit or 5-digit zip code or a postal code. And you say, for each postal code, how much demand do I expect to get? Or you may go at a higher unit, you may look at cities. So you may say, okay, 90% of the demand for my product comes from, medium to large size cities in the US. Maybe you're an online seller, or maybe you're something like Amazon. You have a website, but you have distribution centers to fulfill online orders. And so you might look at cities and estimate the demand for each city based on its population, and then the number of cities in the country, medium to large size or whatever size you're looking at, would become your demand points. But each city aggregates demand for the entire city and surrounding areas. You might go by counties or states. If you're doing a very high level model, you might say each state is a demand point, and you look at where most of the population in the state lives, like one of the large cities or metropolitan areas, and maybe mark that point as the location of the demand, and you aggregate the demand for the whole state to that point, so that point represents your demand for that region. You need to give these models potential locations of facility sites. So you can't just say, okay, here is where my customers are located, here's where my supply switches are located, and you just find me coordinates of where to put my distribution centers or factories and things like that. You have to give it a list of possible locations. Here again, usually you don't give it exact addresses. You're going to specify either a zip code or a state or a city, and then within that state or county or zip code, the exact address you will identify based on other considerations like the price of the land, or access from a highway, things like that. Okay, so when you run the model at a high level, it'll tell you, okay, open distribution centers in these states or in these cities, meaning in the city or nearby the city, and then the exact address you'll find depending on which sites are available, and so on and so forth. You need to know cost data, so material cost, labor cost, handling cost, inventory cost, facility cost, like fixed facility costs. You need to know the transportation rates between any pair of locations. So between all customers and all potential sites for distribution centers, you need to know the transportation rate. Between factory and distribution centers, you need to know what's the transportation rate. By rate, what we mean is the transportation cost per unit per mile. So how much does it cost me to ship 1 unit of product from a factory to a distribution center per mile? And then as you try different distribution center locations, you can compute the distance and multiply the distance by the volume moving along that in that direction with the rate to get the total transportation cost. We'll do examples, so all this will make a lot more sense when you look at the actual examples. For site cost, facility site cost, you need to know the variable cost. So if some unit goes into a distribution center and then later it flows out, it has to be handled, offloaded from a truck, put in a shelf or rack, then picked again, put in another truck. All that incurs cost, and then there's holding cost for the time it's spent to the DC. So you need to know all of those costs so that when units flow through your sites, you can add that cost to them to keep track of your total cost. And then anytime you have a facility site, whether it be a distribution center or a factory, you're going to have a fixed cost. So you'll have some staff, like management staff, you'll have some property taxes, utilities, and these costs don't really depend on the quantity of product flowing through the DC. So whether you move 10,000 pieces through a DC or 9,000, most likely your utility bill is not going to change much. Most likely the salaries of the management staff is not going to change much. And so those costs are like fixed costs that you need to keep track of if you're going to use that site. So any site you use for your solution to meet demand, you have to include the fixed cost as part of the total cost. Taxes and tariffs, so these might be incurred on things that come into the country, or different states may have different taxes. So if something goes to a particular customer, it might have a certain tax to be imposed. And then you have customer service aspects, desired response time, and other customer service factors. So you might say, okay, I want to come up with a logistics network which can supply my customers within 2 days of them placing an order, or within 1 week of them placing an order. The more you relax the response time, the less warehouses or distribution centers you'll need and less cost you'll have. If you need quick response, you'll need to have a distribution center close to all the customers, so any customer that places an order, they can quickly get a response. And then you may have other constraints, such as these existing facilities cannot be moved, certain regions to avoid, things like that. and you can put them as constraints if you have constraints like that. So when you're working on large scale problems, like real life scale problems with many different facilities, your model may become more complex to be done in Excel, although I've seen people do very large models in Excel as well with hundreds of variables. And for small to medium sized companies, Excel may be sufficient, but a lot of times you want to use a professional software to do network optimization. Two popular options are any Logistics and IBM iLog Cplex. IBM iLog Cplex is more complex to set up, needs a little bit of scripting language, is really powerful, and it's actually used as the backend by any Logistics. So any Logistics is a nice interface on top of IBM iLog Cplex where you can more easily specify your model, and then it runs the model on IBM iLog Cplex. So these are a couple of options you could use to solve large models. Although you can do a lot with Excel as well. So all of the stuff we talked about, the kinds of inputs and cost, these software can handle all of that. So let me show you some example outputs. So on the left with the map of the United States with the states labeled with the names, that is one of the outputs of any Logistics. It also gives you outputs in tabular form, looking at cost and how much stuff is flowing. You can see that the purple warehouse is where material comes in from overseas, and that becomes like a national distribution center, and it ships out stuff to customers, which are those blue circles, and also it ships out stuff to other regional distribution centers, the red circles, which are 3 of them. And then this is the solution from running a network optimization model, where it's telling you where the red circles need to go and which red circle needs to serve which customer, the blue circles, for you to minimize your total cost. Okay. On the right as well, this is also a similar output where the black squares with the number 1 in the center of these colored lines, stars made by colored lines, is the location of distribution centers. And then you have lines going from the distribution center to demand points. So the model tells you which demand point should be fulfilled by which distribution center, as well as tells you how many DCs you need. So in the picture on the right, we need 1, 2, 3, 4, 5, 6 distribution centers. It also tells you the locations of the distribution centers. And so it really sets up the whole network for you. So once you're done, you know where to open your DCs and which DC, which customer's orders will go to which DC to be fulfilled. Okay. And so you can see this is the graphical output, and obviously the software will also give you output in tabular form, where it would list all of this information, location of the DC, how much product flows for which customer from which DC, and so on. Now there is a trade-off between service level and cost, and you'll see that more in the lecture we do on different types of logistics networks. We'll look at some common types of logistics networks. What happens is, if you want to give very fast delivery service to the customer, you need to have your distribution centers close to the customer. And so to give really fast service, like Amazon Prime service, you need to have a lot of distribution centers. But the cost obviously goes up the more distribution centers you have. And so that may not be the lowest cost option. So if you want to optimize your network to provide a very high level of customer service or responsiveness to customer demand, you may get a solution with many distribution centers. And if you tell the model just to optimize for total cost and not worry about responsiveness as much, you will get a different solution. So if you compare the solutions on the picture, and if you look at the optimal network for service, optimizing for service, i.e. being responsive to the customer, It has, let's count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It has 12 distribution centers to serve the same customers and demand that the picture on the left that's optimized for cost is serving with 1, 2, 3, 4, 5, 6 distribution centers. So to optimize for service, our number of distribution centers doubled. And when we're optimizing for cost, our number of distribution centers is half, 6 versus 12. Now, why would the cost be much less for 6 distribution centers? Well, one, you have aggregation benefits of inventory that have fewer locations. You have fewer facilities, so fewer facility fixed costs. And you have economies of scale because your warehouses or DCs are larger, handling larger volumes, so you can make a business case for more automation in them, and the handling costs and so on might be lower in 6 large DCs than 12 small or smaller DCs. Okay. But it's not that you have to just pick one, that you can just optimize only for service or optimize only for cost. You can do a mixture. So you can say, I want my customers to get delivery within 5 days. And then once you meet this criteria of giving my customers delivery within 5 days, then optimize for cost. So you make it a constraint, make sure all deliveries are complete within 5 days, and then you just optimize for cost. So that way you've fixed the target service level. This is the service level I want. And then with that service level in mind, you optimize. And then if you don't like the solution or it's too expensive, then you can relax the service level constraint and say, okay, maybe I'm okay with delivering within a week. And then, okay, how about let's change this constraint to allow delivery within 7 days. And then what's the lowest cost network I get now? Or if you feel that the network you got with allowing 5 days for delivery, too many customers are sitting right at 5 days, whereas you wanted most of them to be within 2 to 3 days and very rarely go to 5 days, you might say, okay, no, this is not good enough. I'm going to say I want 80% of the demand to be met within 2 days, and then all demand to be met within 5 days. So most customers are within 2 days. And then given these constraints, now optimize the total cost. Okay, so you're trading off the service and cost by running, the model with different settings, and then you can pick which trade-off you like best. Now you'll see this again when we discuss types of logistics network, but this picture with multiple graphed lines looks a little bit complicated. But what it's trying to show you is that there is a sweet spot where you are giving sufficient service to the customers and also optimizing your cost or maximizing your operating profit. So the line at the very top, it says optimal margin and service mix sweet spot. That is your profit line. Okay, and you can see the profit grows as you increase number of facilities. That's the x-axis initially. Why? Because as you increase the number of facilities initially, you're able to satisfy more and more demand, because some demand may be time sensitive and may not come to you if you're going to deliver to them after a week or something. But beyond a certain point, your benefits of demand, there's no more increase in demand, and you're only increasing your cost by opening too many distribution centers or other facilities, and your profitability starts to fall. Total logistics cost, the line in blue, has the opposite type of shape. The cost goes down for some optimal number of facilities, but then the cost starts to go up. Okay. Why does the cost go down for a certain number of facilities initially? Because when you are closer to the customer, your outbound transportation cost falls. And so initially you're benefiting from transportation costs falling as you open more facilities and your distances get smaller to the customer from the distribution centers. But eventually, beyond a certain point, the facility cost starts to dominate. You have too many small DCs lying around with too much facility costs, too much inventory safety stock type of costs, and then you're not really benefiting from the benefit to transportation cost is eaten up by all these increase in other costs, and so your total cost starts to rise. Okay? So by adjusting your service level and rerunning the model, you're trying to find the sweet spot where your total cost is low, your margins are good, and you're offering a sufficient level of customer service. And it's not easy. You need to understand and have some experience with these things, and also play around and read on the model, do a lot of what if analysis. What if I do this? What if I do this? Yeah. And what you're trying to balance is your operating expenses and working capital, which are these chips in blue, these blue boxes, with the service level benefits. So order turnaround time and delivery frequency, customers like that. Like let's say you have retail stores, you can give them frequent delivery, quality of service, stocking strategy, inventory availability. All of these are offering a high level of service. But to offer this high level of service, you need more inventory assets, you need capital investments, you need warehouse and transportation expenses, and so on. And so you need to balance both sides, service and cost. So when do we do an optimization study? We talked about this already, so I'm just going to go through it quickly. So merger and acquisition is a big reason to do this optimization studies, because you might want to merge or close some facilities. Downsizing or growth of a business, you're growing, you have demand has gone up too much or demand has fallen too much. There could be competitive pressures to reduce costs. So maybe other competitors have come in and they have lower costs than you. They're able to give more discounts to customers, and now you want to reorganize your logistics network to really focus on costs and become more cost efficient. There could be changes in customer service level requirements, maybe because of changes in customer preferences or competition offering a higher level of customer service. So you want to reorganize your network to be able to match that level of customer service in terms of delivery times, responsiveness, and so on. There could be new market opportunities, expanding to new areas, expanding internationally to new countries where you were not there, you were not in those countries operating there before. Changes in customer base or supply base. So maybe you change your suppliers and now your production plant is kind of located far from your new suppliers or something, and you want to see if there's a better site to locate your production, things like that. Large changes in transportation costs that are expected to hold for many years. So because your model optimized, the total of transportation cost, facility cost, fixed cost, and all of these things. And now those trade-offs have changed because transportation costs have increased. And so it might be worthwhile to have more facilities, have a little bit higher facility costs, but really reduce your transportation expense because these facilities are closer to the customer. So the trade-off between these costs is going to be different now that the transportation rates have gone up. If they have gone up and you expect them to stay high, it's not a temporary spike. Then you would want to redo the optimization study to see, if opening new facilities is going to help you reduce your transportation expense. Large changes in interest rates can also influence this because the interest rates impact the cost of holding inventory. So if you have fewer distribution centers, you're more efficient on inventory because your inventory is centralized in a few places. And so you don't need as much safety stock with centralized inventory as you need with inventory in many different places. And we'll talk about this more and why this happens in the lecture on types of logistics networks. But for now, you should know that if you increase the number of facilities, your safety stock requirements go up. If you reduce the number of facilities, your safety stock requirements tend to fall. And so if your inventory gets more expensive because of higher interest rates, you may want to reanalyze how many facilities you need to have. This is a pictorial representation of a logistics network. So you have supply sources on the left, okay, which go into, so the supply could be vendors, could be a factory, could be imported product on a ship. That supply goes into some large distribution centers who then feed regional warehouses which are close to the customer, who then feed either the customer directly or feed retail stores. Okay, so you have a multi-echelon or multi-tiered logistics network. Now, modeling the transportation rate is really important to get it right, because in all of these models, you're going to specify distances between points and then specify a transportation rate that's going to be dollars per unit per mile. If you move 1 unit of product along a particular route 1 mile, that's how much money you spend. Or sometimes you specify the transportation rates in dollars per unit for each route. So if you go from DC in this city to customer in this city, this is how much you spend per unit without factoring in the distance is already factored in. So you don't have to multiply by the distance because it's given for a pair of 2 points. So whether you specify transportation rate as dollars per unit or dollar per unit per mile, depending on your modeling approach, figuring out the right transportation rate is really key, because if this rate is not accurate, the model results are not going to be accurate, obviously, because transportation cost is a big part of the cost that the model is trying to minimize. A good way to get these rates is, let's say you have DC shipping to customers. These could be retail stores or other regional DCs, or this could be factory to a DC. These are line hauls. Truck takes a lot of stuff to the other site and comes back. And so here you can just look at historical data, historical shipments, if these sites already exist. Or you can get historical data from a transportation company and tell them, okay, if you've been shipping truckload shipments on this route from this city to this city, what's the expense been over the last 3 years? What's the average shipment cost? So you can get some historical data either from shipping companies or from your own operations, and then try to estimate the transportation rate based on historical data. Now, if you are traveling to a town or a city or a county and hitting multiple retail stores or customers before coming back, then your transportation cost between this county or city that is considered one demand point and the DC will depend as before on the distance and whether you're using truckload or LTL shipments, but it'll also depend on how many customers you hit on each trip. Because the more customers you have to hit, the more cost it will be, because the truck has to stop and be offloaded and then travel to the next customer. And so again, you can use historical data if you've already been doing some of these deliveries. You can say, okay, historically, from if my DC is in this city and customers are in this zip code or this county, and I'm on average, my truck goes and does 5 stops, hits 5 customers, then on so such a trip, my average cost is this much, and then you can determine the transportation rate. Okay. If you don't have historical data, again, you can sit with a transportation company and say, okay, let's imagine this is my product. This is how it's going to be palletized. I want to ship this many pallets from this zip code to this zip code, or this county to this county, and it's going to hit 3 delivery points or 4 delivery points. What's going to be the transportation cost for this whole thing? And then you can divide that by the number of units you're shipping to get a dollars per unit shipment rate, or also divide by the distance D between those 2 zip codes to get the rate in dollars per unit per mile. Okay. So again, historical data, or just doing what if analysis with a transportation company, asking them how much would you charge for this sort of a load going from here to here, you'll be able to gather this data and get your transportation rate, which is one of the key inputs into the optimization model, because if this is not accurate, the results of the optimization model will not be accurate. Okay, let's do some examples. Okay, so the first example we're going to do is we have this geographic region shown in this sort of square or rectangle, and we need to figure out how many fire stations we need and where to place them. Now, the districts are marked. We have 16 districts, and a fire station serves the district it's opened in and any neighboring district which shares a border with the district. If a fire station could only serve the district it's opened in and no other district, the solution would be simple and straightforward. You need to open a fire station in every single district, and you need to open 16 of them, 1 in each district. But that's not the case. If we were to open a fire station in District 1, it would also be able to cover District 2 because it shares a border, District 5 because it shares a border, as well as District 4 because 1 and 4 share a border. However, a fire station in District 1 cannot serve District 6. It cannot serve District 3. Okay. So what we're going to do is we're going to figure out each district has to be covered at least once, has to be covered by at least one fire station. Okay. So we are going to, we're not given the cost of the facilities, but we are just told that the cost increases with the number of fire stations. So don't open fire stations you don't need. Only open enough fire stations that every district is covered by some fire station. So you need to minimize the total number of stations needed while providing fire station coverage to all 16 districts. Okay. So the first step in this source of problem solving is to figure out your decision variables. What are the variables that are going to store the information about your solution? In this case, we need to have 16 variables, okay, x1 to x16, whereas each variable is going to be a yes-no variable, what we call a binary variable, a 0-1 variable, 1 being yes, 0 being no. So each of these variables will store a 1 if a fire station should be opened in the corresponding district, or 0 if no fire station should be opened in the corresponding district because some other fire station is covering it. Okay? So x1 would be 1 when we open a fire station in District 1. x1 will be 0 otherwise. Same for x2, same for x3, and so on. So we need x1 to x16, 16 of these variables, it can be 1 or 0, to keep track of where we are opening the fire stations. Now, we also know that a fire station in District 1 is going to provide covers to District 1, 2, 4, and 5. So we note that down. Similarly, a fire station in District 2 will provide cover to Districts 1, 2, 3, 5, and 6. So you can see that listed here. If we open a fire station in District 3, we provide cover to 2 and 3, obviously, because it's open there, 6 and 7. And we go down the list and we write down if a fire station is open in a district, what other districts does it cover. So if you look at 16, the lost district, if you open a fire station in 16, you obviously cover 16, but you also cover 13 and 15. Okay. So our model now takes this shape where we want to minimize the sum of x1 to x16. Okay. Why? Because each of these x's is 0, 1. When you sum up all of these x's, you get the total number of fire stations you're opening. And you want to minimize that. That was our objective from the beginning, that we want to minimize the number of fire stations we have. Now, if we don't do subject to and don't give it constraints, solver will just open 0 fire stations because there's no constraints forcing it to keep some fire stations open. So this coverage values will become our constraint. The first row of this table, we want to make sure that x1, x2, x4, or x5, one of these 4 x's is 1, at least one of them. Because if one of these 4 x's is 1, if you have a fire station in District 1, 2, 4, or 5, then District 1 is covered. So to cover District 1, we write this equation that x1 plus x2 plus x4 plus x5 must be at least 1, must be 1 or more, which would ensure that District 1 is covered by a fire station. To ensure District 2 is covered by a fire station, we look at the second row, what is covered if we for 2 to be covered, there must be a fire station in District 1, 2, 3, 5, or 6. Okay? So that's that. x1 plus x2 plus x3 plus x5 plus 6 must be at least 1. If the sum is 1, that means the second district is covered by a fire station. The sum is more than 1, like 2, then it means that that district is covered by 2 fire stations. And that we have to allow for that because sometimes you may be opening fire stations to cover a district that nobody else is covering, but that fire station may also double cover a district that's already covered. And then there's no way around it. You have to open it to provide coverage to the uncovered district. So that's why we have greater than equal to 1. We want to allow a district to be covered by more than one fire station. Obviously, it's not ideal because we want to minimize the number of fire stations. So we'll only do it if it's absolutely necessary. Otherwise, we'll try to be minimizing the number of fire stations. So we'll have 16 of these constraints. Each constraint, which is under the subject line, each constraint is an equation with an inequality, which makes sure that each region is covered by at least one fire station. And then we have another constraint that the xj variables must be only 0 and 1. You can't have a 2 or a 3 in an x variable because they are just, turning on and off whether there's a fire station there or not. And so let's look at how to build this model in Excel. So this is how the Excel table looks like. Okay, over here we have the 16 districts labeled. These are just labels. These cells don't do anything. Okay. And here in the yellow are my 16 decision variables. Let's make it green. Okay, in the green are my 16 decision variables. This is x1, the first cell. This is x2, this is x3. Now, you don't have to enter any values in the beginning. You just set aside 16 cells to make to be your decision variables. And these will be called changing cells when you go to Excel Solver. Now, one way to enter the first constraint is you want to pick x1 plus x2 plus x4 plus x5. So you could say here something like constraint 1, and then let's pick these values. You will pick x1, okay, plus x2 plus x4 plus x5, okay, x1, x2, and you can actually write labels here so to make it easier to read which one is which. Okay, so x1, 2, 4, and 5. X1, X2, X4, and X5. You pick them. So that's going to be the left-hand side of this constraint. That's this right here. Then you're going to say that has to be bigger than or equal to 1. And so I'm just going to add a label here, quotation mark, bigger than or equal to, and type 1. But I'll have to specify this inside the solver interface. I'll show you in a minute. This by itself doesn't do anything. It's just a label for me to read. But what I'm saying is this sum has to be bigger than or equal to 1. Okay, that's going to. They're going to put constraint 2 like that here, constraint 3. Okay, another way to do the exact same thing is to have a row which is 1 whenever you want to pick up that x and 0 otherwise. So for the first constraint, we need x1, x2, x4, and x5. These are the 4 you want to pick up. So we make those 4 1. x1 is 1, x2 is 1, x4 is 1, x5 is 1. The rest all become zeros. And then if I multiply this 16 cells by these 16 cells, the zeros will zero out the cells I don't need, and the ones will pick the cells I need, and then I can do a sum. So I can say here, okay, sum product of the first column with this. And actually I'm going down by the column. So I'm saying x1, x2, x4, x5. That's what I'm going to pick. That's my first constraint. So if I do a sum product of this column with this, I get exactly this thing. I get 1 times x1 plus 1 times x2 plus 1 times x4 plus 1 times x5 summed together, and everything else is zeroed out. And then for the second constraint, I do the same thing. I pick up x1, x2, x3, x5, and x6. Those are the ones. And I zero out everything else. And so only those x's get summed and come here. This is my second constraint. My third constraint. So it's much easier to just do sum product of these columns than to kind of individually select the x's for each constraint. Okay, so that's the approach I'm going to take. So this here, all of these, okay, is going to be the left-hand side of my constraints, right here, this part, this part, this part, all the way to this part, okay? And the right-hand side is just a constant 1, so that's what I've typed in here. This is my LHS, left-hand side, LHS, and then this is my RHS, okay? Right-hand side, which is just a constant 1, because all of these have to be bigger than or equal to this one, okay? And now, to total the number of fire stations, I just sum my variables, x1 to x16. Their sum gives me the number of fire stations. So how to set up and solve? You go to data, data, and if you don't see the solver, but here, if you're on a Mac, you have to go to tools and enable tools and add-ons and enable the solver add-on in Mac. In Windows, you have to go to file and go to options at the bottom. And then in options, you have to go to add-ins. And then here you have to do manage Excel add-ins and enable the solver add-in by hitting this tick mark, enabling it and hitting OK. And then you get the solver button in your data tab. Okay. And so you hit the solver button. And in the solver, you have 3 areas. The first is the objective function. What do you want to minimize or maximize? That's this right here. I want to minimize the sum of fire stations. Okay, so I choose min. By default, it might be max. Make sure you do it min because you're minimizing it. Because if you look back, you want to minimize this whole thing, minimize this sum. Okay, so in Excel, we choose minimize. The sum is in B27 right here. By changing cells, those are your x1 to x16. So you select these green. So you select these 16 cells. Those are the ones you can change. And then you specify the constraint that all of this left-hand side, which is B21 to Q21, has to be bigger than or equal to this. So let me show you how you specify this constraint. Let me delete this. You would add a constraint. So the cell reference is the left-hand side. You select your left-hand side. Okay, this has to be bigger than or equal to, and the right-hand side is just the constant ones. And you hit add. And you hit cancel because you're not adding another one. So that's your constraint. And the last constraint you need is you go add and you select all of these decision variables and they all need to be binary. So you choose bin and you hit OK, and that adds the binary constraint. So I did it twice. I'm going to delete one of them, but that's where the binary constraint. You're going to pick simplex LP and make unconstrained variables non-negative because my x's can't take negative values. So you click that, choose simplex XP and hit solve and keep solver solution OK. And that's your solution. You need 3 fire stations, district 4, 6, and 15. Okay. So if you look at that, district 4, 6, and 15, they get the fire stations shown by red circles. And total number of fire stations is 3. The green districts show you which ones are covered by the fire station in district 4. The blue area is the area covered by the fire station in district 6. And this magenta or purple area is what's covered by the fire station in district 15. Okay. So that's a very easy logistics network type of model, picking certain facilities to provide coverage. So these districts are like our demand, and they are covered by a fire station which is in the district or in a neighboring district, and you provide that coverage by opening 3 fire stations. And this is our minimum cost solution, because the more fire stations we open, the more cost we have, and we can't go below 3 because our service requirement to the customer are that I'm going to be in your district or the neighboring district. So we can't go do with less than 3. Let's do another example, more closer to an example where product is going to be moving through a network, where we have petrochemicals company and we have to supply demand in these 5 regions of the world. And now we're going to talk about, where to set up our facilities to supply demand. Okay. Okay, so in this example, we have Sun Oil's a petrochemical company with worldwide sales. They've divided their global sales operation into 5 regions: North America, South America, Europe, Asia, Africa. The VP of supply chain is torn between 2 strategies. There's a local strategy where you locate a manufacturing plant in each region. It's advantageous because it reduces transportation costs, because you're just supplying the demand in each region from a plant within the same region. However, it may lead to setting up many small plants that do not benefit from economies of scale, because you have 5 regions, you'll need 5 small plants. The other strategy is to have less than 5 plants and get economies of scale from having larger plants. But then your transportation costs will be higher because each region does not have its own plant. So some regions, you'll have products shipped from another region. So you, as an enlightened student, inform the VP that you build an Excel model to formalize this trade-off between costs and find the optimal solution. So here's some data you're provided. Demand per region in millions of units. So North America has a demand of 12 million units. This is usually annual basis per year. South America has 8 million units of demand. Europe is 14. Asia is 16. Africa is 7. Then you have some costs. They're given in the table below. Okay. And so these costs are a sum of production and transportation costs. So if North America region plant is supplying North American customers, the cost is going to be $81,000 to produce and transport 1 million units from North America to customers in North America from the plant in North America. If the plant in North America is going to serve customers in South America, 1 million units, the cost of that will be $92,000 to produce and send 1 million units to South America. So why did the cost go up? Well, maybe the production cost is going to be still the same, but the transportation cost increased because you're shipping to a longer distance. Okay, and so you can read this table like this. So let me give you an example. So $101,000. So each number here is in thousands of dollars. $101,000 is what it cost to have North America supply 1 million units to Europe. Okay. Okay. Now you might be saying this is a very high level problem, right? We're just evaluating which region to open in. It could be a first cut way we attack this problem, and we say, okay, let's pick which regions to open plants in. And then you might say, okay, for these regions, I'm going to pick the 3 most ideal locations, or 3 options, or 5 options, and then run another model, with those options to see where I need to open my manufacturing plant. Or in real life, because this is an example for a class, you might just pick 2 or 3 promising sites in each region and have a model which is, instead of 5 by 5, it's 15 by 15. So you have North America 1, North America 2, North America 3, South America 1, South America 2, South America 3. So each region is distributed into 3 regions. And you could do Asia because it's so big into 5 regions. So you have Asia 1, Asia 2, Asia 3. So you could just do it like that. And that will give you a narrower picture of exactly which portion of each region to open the plant in. So it's not to say that you have to solve this problem like this. You can obviously split each larger region into smaller regions and then increase the size of this table, figure out your costs, and then read on the model, and then it'll pick where to open the factory in which smaller region or sub-region as well. Okay, but we are doing it at a high level for now. Now, the plant, we also have another decision to make when we pick a region, whether you want to open a plant with small capacity, which is 10 million units per annum, or you want to open a large plant, which has a capacity of 20 million units per annum. And then the fixed cost for each size in each region is given. So North America, the small plant has a fixed cost of $6,000, so $6 million. And if you go for a large plant, the cost increases to $9 million, 9,000. You'll notice that we doubled the capacity, but our fixed cost did not double. That's because of economies of scale. So a double plant does not cost twice as much to run. And so South America is cheaper to build a plant there, and it's still cheaper. The large plant is also cheaper than North America. Africa is the cheapest in terms of fixed costs. Okay. And so not only must the model decide where to open the plants and how many plants to open, but it also must pick whether you want to open a small plant in that region or a large plant. Okay. So let's look at our model. we're going to need all of these variables to keep track of the stuff, because there's a lot of stuff happening here, you know. We have to figure out where to open the plants, whether it's small or large, and the plant, each plant, if you open more than one plant, then you have to say which regions will be served by which plant. So we have N, the number of potential plant locations, which is 5, you know, the 5 regions. And M is the number of markets or demand points, which is also 5. So we have 5 regions of demand, the same 5 regions for plant locations. Okay. It doesn't always have to be the case. You could have a location, for example, Greenland could be a location for a plant, and then you don't serve demand in Greenland, it's just used to export stuff to other regions, for example. So you could have different number of regions for plant locations and a different number of regions for demands in the general case. But here is the same. The same regions are both for source for production, and the same regions have demand. DJ is the annual demand from market J. For example, D1, the annual demand from North America, is going to be 12 million units, as we saw. Ki is the potential capacity of plant I. So Ki is going to be 10 or 20, depending on if you open a small plant or a large plant. Fi is the fixed cost of keeping plant I open. That's given here. If it's a small plant, the fixed cost will be 6,000 for North America, 9,000 here. So, you know, these numbers will be represented as Fi. Cij is the cost of producing and shipping 1 unit, which is for us is 1 million units, because we're working with millions of units, from plant I to market J. So this is your Cijs. 81 is C11, 92 is C12, 101 is C13, 105 is going to be C32, and so on. This will be C55. Okay. So that'll be a Cij. You could index it, right? And then Yi is if plant I is open, 0 otherwise. You have 10 Yis. Why? Because you have 5 small plant options, Y1 to Y5. Then you have 5 large plants options, Y6 to Y10. And Xij is how much quantity is being shipped from plant I to market J, because not all plants will serve all markets. So some of the Xij will be zeros, saying that no product flows from this plant to this market, and that will help us assign which markets are being served by which plants. Okay. Now we can just start setting it up in Excel, but I'm just going to show you the mathematical notation as well. You don't have to write it down. But it's useful to understand what is happening. You can just go build it in Excel. So we're going to minimize the total cost. So this cost right here, the Cij times Xij, is our production and transportation cost, because that's going to be these numbers multiplied by how many units are flowing from North America to North America, how many are flowing from North America to South America, and so on. So the unit flow, the volumes flowing in the network, times these costs will give us the total production and transportation cost for our production and shipment in the network. That's this part here. The sigma, this big sigma term here, just means add stuff up. So we add stuff up across the rows and across the columns. The first sigma is adding stuff up across the rows like this. And then the second sigma is adding stuff up across the columns. So you add up across the whole table. Okay. So that's our production and transportation cost. Then this part here is adding up all the fixed costs. So Fi small is the fixed cost of a small plant times Yi small, which is going to be 1 if a small plant is opened in North America or 0 otherwise, plus fixed cost of a large plant times Yi large. So you're going to have 5 of these. These 2 terms are for 1 region, and then you have 5 regions. So you're going to have 5 of these added up by the sigma. Okay. So don't worry, it'll make more sense when you see it in Excel. And then this is what you want to minimize, the total of the fixed cost plus the production and transportation cost. That's the total cost you want to minimize. Now we want to have some constraints, because if you don't have any constraints, the model is smart. It will produce and ship 0 quantity and have 0 cost. And say, haha, I got done with 0 cost. But yeah, you're producing and shipping nothing, you're not meeting customer demand. So we have to put in a constraint to make sure we meet customer demand. So we have to say that the sum of each of these columns must add up to equal the demand of North America, because North America is getting product from one of these 5 regions, or all of them, or some of them. So if you sum up all the product flowing into North America from these regions, that should be at least 12 million units, because we need to satisfy the demand for North America. Okay, so that's this. The sum of each column must equal the demand for that region. Okay. We can say bigger than equal to as well, but we'll never ship more than a region needs, because it costs us money to ship something. And if it's not needed by the region, why would you ship something if they don't need it? Okay, then we want to make sure that what we ship out of a manufacturing plant, which is the sum over a row, has to be less than equal to the capacity of that region, because each region can have only one plant, either a small or a large plant. So if the first region has a small plant, then everything North America ships out across the row to any region should at most add up to 10 million units. And if North America has a large plant, then the sum of the row should add up to 20 million units. Okay, so when you multiply that K is 10 million for a small plant times Y will be 0 if the plant is not open, 1 if the plant is open. So this will say whether the plant is open, it'll give you a 10 million capacity. If it's closed, it'll give you 0. And if the small plant is 0, the large plant might be 1, so it might give you a 20 million capacity. Or both may be 0, and then you have the plant is just closed, so that region can't ship out anything. There's no plant there. And then we want to make sure that we don't open both a small and a large plant in the same region. So we want to make sure that the small and the large for the same region are 1 or 0, but never 2. We don't open both small and large, because Y can only be 0, 1, each Y. And then Y has to be 0, 1 only. So that's our model. And then we can set it up in Excel. I'll show you the Excel file. Okay, so here is the data. First, I have the input section of my model. This is the table right from the slide. You can copy paste it. And under each column, I have a demand row where I put the demand. So North America region needs 12 million units. South America region needs 8 million units, and so on. These are the demands. And across here, I put in my capacity and my fixed cost. So the plant and the supply, if I'm supplying from North America, if I open a plant with low capacity, I have capacity of 10, and this is my fixed cost. If I open a high capacity plant, my capacity for North America will be 20 with a fixed cost of 9,000. Okay. So this is all data. This is all data. There's no formulas, nothing else going on here. So this input section is all data. I just took the data from the question, put it in a nice tabular form. It's going to make it easier for me to write my Excel formulas. Now my decision variables, I need, if you go back to the slides, my decision variables are going to be the Xij. These are my decision variable. And then the Yis and the Yil, which is whether you open a plant or not, and the Xij is how much quantity moves along that arc. So this is my Xij. This is X11, X12, X13, X14, X15, X21, X22, X23, X24, X25, on and on. This is X55. These are my Xij, which correspond to the cost figures of Cij up here. I'm going to have to multiply these values by these cost figures when I'm calculating my cost. So corresponding to my cost for each supply and demand arc, I have Xij, which capture how much product is flowing across that source and demand arc, source to demand. Then this is my Yis, Y1s, Y2s, Y3s, Y4s, Y5s. This is my Yil, Y1 large, Y2 large, Y3 large, Y4 large, Y5 large. Okay. If this is 1, then that means that a small plant is open in this region. If this is 1, it means a large plant is open in this region. So right now, this is 1, which means in South America, we want to open a large plant. This is 0. Total plants in each region is this plus this. So this is just a formula adding up these two cells. And because I don't want the sum of these two to be 2, it has to be less than or equal to 1. I can have 0 plants in a region, or I can have 1 plant in a region, but this number should never be 2. This is on the left-hand side of my constraint. The right-hand side is right here. This left-hand side, which is the total number of plants in the region, must be 0 or 1, but never 2. Then I want to make sure that the total quantity supplied to a region, supplied from a region, okay, total supplied from a supply region is less than equal to the capacity. So for example, South America, I opened a large plant, so my capacity is 20 million. So I can only supply 12 plus 8, 20 million. I can't make this 2. I mean, I can, but it's violating the constraints. It's not a valid solution anymore. I have to keep it 0 because I already supplied 12 and 8, 20, and I have no more capacity to supply these other regions. Don't worry, Excel will pick the values of the green and the blue cells. You don't have to type it in. You can make it all zeros to begin with or just leave it empty. Okay, so total supplied by North America is going to be the sum of this row, and that has to be less than equal to, my capacity will be this times 10 plus this times 20. So if you look here, right here, see, K is 10, and Y1S is that blue cell 0 or 1, and KIL is 20, and YIL is the other blue cell which is 0 or 1. So this times 10 plus this times 20. So you can see that this is your total capacity. Okay, 10 times this 0 plus 20 times 0. Because I don't have any plant open in North America, my total capacity is 0, so North America must ship out exactly 0. Can't ship out anything. Total capacity for South America must be less than the capacity of South America. So this times 10 plus this times 20. So whichever one is 1, it picks up that capacity. Same thing for each region. Okay. Then the sum of the column is how much is going into North America. So North America is receiving 12 million units because that's the sum of 0 plus 12 plus 0 plus 0 plus 0. So this sum is what North America is receiving, and I minus the demand of North America to calculate. I do the demand in North America minus what it's receiving to calculate any unmet demand. So my unmet demand is 12 million minus the sum. 12 million, which is requirement, minus what North America is receiving is my unmet demand, and I do the same thing. And then I'm going to put in a constraint that unmet demand must be 0. I want to meet all of the demand. I don't want to leave any demand unmet because my total capacity possible is 20 times 5, which is 100 million units, and my total demand is only 57 million units. So obviously, if I open all the 5 plants, I'm going to have more capacity, so I can meet all the demand. Sometimes even if you open all the plants, you can meet all the demand, then you may say, okay, unmet demand should not be more than 2 million per region or something like that. But here we have, if you open all 5 plants, we're going to have enough capacity to meet all the demands. We're going to say unmet demand must be 0. Okay. And then the cost function is going to be all these green cells, some product with all of this. And then the fixed cost is going to be these, some product with these, and these, some product with these to capture the fixed cost. Because if you remember the slide, our cost is the fixed cost part, which is the dummy the 0, 1 variables, the blue ones, y times the fixed cost values, and then the transportation and production cost for each arc times the volume flowing on each arc. So the green cell, this is the volume flowing on each arc, from source to destination. This is the production and transportation cost for each arc per million units, and this is how many million units are flowing on the arc. So this sum product with this gives you production and transportation cost. This sum product with this gives me fixed cost for small plants, and this sum product with this gives me fixed cost for the large plants. Right now I don't have any small plants, so that's going to be 0. So that's my formula right here. Sum product of the green cells with this, sum product of this with this, sum product of this with this, added all together. Okay. Now to solve this, now this is all set up, then you go to data, solver, you're going to specify to minimize your total cost right here. Make sure you set to minimize. By changing cells, okay, you're going to be changing all of these cells, blue and green. Now you go to B14 to H18. This is B14 all the way to H18. Okay. So I changed this wrong thing. I need to minimize this, not to minimize all of that. Okay, and then the changing cells are your decision variable, which is B14 right here to this H14, which is the green and the blue cells. All of them are decision variables. And then I put in my constraints. So B22 to B26 is right here. Total supplied must be less than equal to total capacity. That's my first constraint. Okay. and unmet demand should be 0. So B29 to F29 must be 0. Then these blue cells must be binary, otherwise it will make them 2 or 3 or whatever it can, technically, or make them 0.5. So we don't want any fractions, we don't want anything above 1, 0 or 1. So we say G14 to H18 must be binary. Okay, and then we say that these plants here, I14 to I18, must be less than or equal to 1 because you don't want to open 2 plants in a country. Okay. Simplex LP, make unscontrollable as non-negative because we don't need to have negative values here. Because if you flow a negative volume, this will make it a negative cost and will reduce your cost. So you have to say make uncontrollable variables non-negative. Simplex LP is what we choose. Solve. Okay, so this is wrong. This has to be just this. Enter. Because you minimize that, so that got changed while I was moving my mouse around. Solve. And keep solver solution okay. And this is the solver solution. You could change, I can delete these cells to show you it's actually working. So delete my solution and solver, go to solver, hit solve, and it will put in those values. So you put in those values. So you open 3 plants, large plants in South America, Asia, and Africa, because those are the cheapest locations. And then my Asia plant is going to serve Asia and Europe. And my Africa plant is going to serve Africa and Europe. And my South America plant is going to serve South America and North America, because this is closer. South America is closer to North America. I should be serving that, not serving Asia or Europe. And so Asia is going to be serving Europe. Africa is going to be serving Europe. Okay. And that's my total cost. This is thousands of losses, $23 million, basically, $23.751 million. And so that is the solution. Now, one thing you have to be careful about. In all of our constraints, so these constraints, the left-hand side is a formula. Okay, it's referring to cells and adding stuff up, decision variables, adding stuff up. So that's a formula referring to decision variables. Right-hand side is just a number, 1. I could have 1 somewhere here, okay, and I could say this equals this. That doesn't make it a formula. That's still a constant because it's not referring to a decision variable. It's referring to another constant. So equals to another constant is just a constant, okay? But if you do equals and you pick a decision variable or something that depends on a decision variable, then that's going to be a formula. So right-hand side is not a formula, it's a constant. Left-hand side is formulas, that's fine. Okay, here, this is my left-hand side, B9 minus some of this column, and my right-hand side is specified as 0 in this constraint. So this is the constraint. So my unmet demand has to equal, so this right-hand side is just a constant, okay? So that's fine. These are all fine, right-hand side is a constant. But if you look at this constraint, okay, these cells here are a formula which depends on decision variables. So this works in Windows, but this would not work in a Mac. Mac does not, if you're using Excel for Mac, the solver in Excel for MacBooks, like Apple laptops, is not going to allow you to have the right-hand side of a constraint refer to a decision variable. So that's easy to fix. What we do is we say LHS less than equal to RHS is going to be 0, okay, and we just copy this label down so we know what we're doing. 0, 0, 0, 0, 0, and what we do is, if this has to be less than this, then this minus this must be less than or equal to 0. So the left-hand side just becomes this minus this. Let me show you in algebraic notation what it means. Okay. So Apple for Mac has this problem. Okay, it's not allowed to say a decision variables or something made up of that, some formula is less than or equal to a formula of a decision variable. But you can move this side to here and subtract it. So you can do left-hand side minus the original right-hand side and less than or equal to 0. This is allowed in Excel for Mac, but this is not allowed in Excel for Mac. So our constraints right now, right here, this less than this is of this form, the not allowed form. This is not allowed on MacBooks, it's allowed on Windows. So we have to do left-hand side minus right-hand side less than or equal to 0, okay? So we do that. Left hand side. This is the left hand side minus original right hand side. Okay. So left hand side minus original right hand side must be less than or equal to 0. So I do that. Left hand side minus original right hand side. I bring them down. Okay. And it's fine. It can be negative because capacity can be more than this. So 17 minus 20 can be negative. That's fine. Negative number percent less than or equal to 0. That's fine. And this is not a decision variable, so it's not going to constrain this to be non-negative. It's only going to constrain these to be non-negative. So these are not decision variable. They can be negative. That's fine. That will be less than or equal to the left-hand side. So now, instead of saying these cells must be equal to these cells, I'm going to say these cells must be less than or equal to 0. So I'm going to go to my solver and delete, I'm going to change this constraint. Instead of these cells, I'm going to pick these cells. And I'm going to say less than or equal to. Now I have options. I can just type 0 here, and that's fine. These are equal to 0. Or alternatively, I can select these because these just have a constant. This is going to work as well. Okay. And now solve, and it works. Okay. Let me close this older model. Okay. So yeah, it works. Okay. You can delete these values and see the model will still give you a solution with this formula that works for Mac as well. Solve, and see, there you go. Okay, so this constraint will work on a Mac because right hand side is just a constant, but this constraint will not work on a Mac. Okay, so with this change, I've saved this file with the Mac in the name, and I'll upload it in the, on Canvas. So you'll have both the Windows file where I'm doing this less than or equal to this, and you'll have the Mac file which is this less than or equal to this. It's a good practice to just do things the Mac way, because that's like a little bit more standardized way where you move all the decision variable terms to the left-hand side, and you only have constants on the right-hand side. So if you can get in the habit of that, then your models will work on Mac and Windows, and that's a good habit to have. Okay. Now this was our solution. Open 3 large plants in South America, Asia, Africa. Total cost was $23.751 million. But what if management said, okay, that's well and good, but we have so much research infrastructure helping us to improve our oil extraction processes, oil refinery processes, and these research labs and universities, they need to have access to a manufacturing plant to study our systems. And so because the research infrastructure is in North America or Europe, we need to have at least one plant in either North America or Europe. So redo your solution and give me the lowest cost solution that gives me at least one plant in either North America or Europe. So what we do here, what we're going to do here is we're going to say total plants in North America plus total plants in Europe, this must be at least 1. So let's do this. So let's do LHS, which is total plants in North America or Europe. That's going to be this plus this. Okay. This has to be bigger than or equal to 1. We need to open at least 1 plant in North America. We could open 2, but at least 1. And so we go to solver, we add a constraint that this total plants in North America and Europe must be, you can just type 1 here, you can just select this, must be at least 1. We do OK, and then we hit solve, and we get a different solution. Now we're opening plant in Europe, Asia, and Africa. So we did get a large plant in Europe, and then this is how the shipment happens. Now Europe is being served by the Europe plant, and the Europe plant is also serving North America, and then the Africa plant is serving South America, a little bit of Europe and Africa, and Asia plant is serving Asia and a little bit of Europe too. And this combined is, so Europe is getting stuff given to it by 3 regions. Europe is supplying Europe, Asia is supplying Europe, Africa is supplying Europe. North America gets all of its stuff from Europe, and South America gets all of its stuff from Africa. So that's our new solution. And our cost went up $26.69 million. So before it was 23.75, 23,751. So if you want to take a difference, the plant in Europe is costing us $2,940,000 because this is in thousands, or $2.94 million. So you can go back to management and say, okay, I can do that, but it's going to cost you $2.94 million a year. Are you willing to pay that to have your research labs access that plant in Europe, and they might say, yeah, that's fine, or they might say, no, that's too expensive, right? But you can do that. So that's the update. And I'm gonna leave this stuff in here, and I am going to go to solver and just delete this new constraint I added so people can run the default one, okay? But this is for the second part of the problem where we need a plant in North America or Europe, okay? So this whole thing, maybe I can color it for that, okay? Okay. So this file would now work on Mac, it will work on Windows, and everything is in here for that problem. So that's just for network design. We solved some, small to medium-sized problems in Excel, but in other parts of the course, you'll be introduced to any logistics, where you'll solve bigger problems with more sites and more customers as well. But hopefully this gave you an idea on the structure of these problems, what sort of the math behind it, and how to do them in Excel.